Hello students, in this lecture we are going to see the density of state in three-dimensional case. So we have seen in one-dimensional case what is the density of state, but here we are going to see density of state in three-dimensional case. So in one-dimensional case we have first of all calculated energy eigenvalues of the one-dimensional potential well, and then we have calculated density of state. Here also we have actually calculated the energy eigenvalues in your previous lecture. Here we will see density of state. So for that purpose we have to consider two concentric, you can say, spheres. So I will draw two spheres. So this is, let's say, one sphere, and this is, let's say, another sphere. Okay, the center of this sphere is same. Let's say this is nx, this is ny, and this is nz. So because values of nx, ny, and nz are only, you can say, positive values that we have to consider. Okay, so that's why we will consider only positive values. Okay, so in order to calculate the density of states of the electrons in the energy range between E and E plus dE, okay, so first of all we will calculate the density of state between in the energy range E and E plus dE, and then if we integrate it we will get total energy density of state in three-dimensional space. So this is n space. So consider a concentric spheres of radii n and n plus dn in the n space. At any point nx, ny, nz with the integer values of the coordinates represents the energy state that we have already seen. So if in order to get that understanding, so En, that is given by h cross square pi square upon, let's say, twice m, okay, nx square upon a square plus ny square upon b square plus nz square upon c square. Okay, this is our energy eigenvalues for the three-dimensional potential well with dimension a, b, and c, and ny and nz are the positive integers. So here the factor, so number of energy states having the energy values between n and n plus e and e plus dE is given by ZE dE, which is equal to 1/8 4 pi n square. This 4 pi n square dn, you can say 4 pi n square is because the surface area of that sphere, and 1/8 part because only positive values, let's say positive values of nx, positive values of ny, and positive values of nz are considered, and that means 1/8 part of this three-dimensional space is considered. That means 1 octant is considered. That's why this 1/8 factor came here. So we will basically start with the energy eigenvalues that we have studied in three-dimensional case. So here n square, which is equal to nx square, ny square, and nz square, where a is equal to b is equal to c. So if we consider a is equal to b is equal to c, our energy eigenvalue, which is given by h cross square pi square into divided by, let's say, twice m into nx square upon a square plus ny square upon b square plus nz square upon c square. This becomes like this. Okay, it get converted like this. So from this equation, if I rearrange this equation, if I take this 2ml square on the left hand side, so here a square, a is equal to b is equal to c is equal to, sometimes it is l. I told you lx is sometimes called as a, ly is sometimes called as b, and lz is sometimes called as c. There are different notations in different books, but don't get confused. All these are for the dimension of that infinite potential well. So if I want to take the value of n square on the left hand side, so n square, which is equal to this twice ml square, will go on the left hand side, and it will become, so if I rearrange it in this equation, I will get this equation. Okay, so thus if I take the square root, that will be n is equal to twice m raised to 1/2 into L upon pi h cross into e raised to 1 half. So I have taken the I have taken the root of this equation. Sorry, I have written here negative sign, but this is not negative sign, it is actually positive sign. So thus n is equal to this value. So if I differentiate it, I will get Tn is equal to twice m raised to 1 half. So this is a constant, L upon pi h cross, that is again a constant, into, then there is only one variable, and that is energy raised to 1 half. So 1 half into e raised to minus 1 half into dE. So that is the, you can say, if we differentiate on both sides, we will get this equation. So this is, let's say, my second equation, this is my third equation. Why I am getting this n square values and dn value is because I have just written Ze dE in the previous slide, which is equal to 1 by 8, that is 1 octant is used into 4 pi n square, that is the surface area of the sphere, into dn. So that's why I want this n square and this dn to get the value of Ze, that is density of state in between energy E and E plus dE. That's why I will differentiate so that's why I have obtained n square and dn value. So I will put this equation number 2 and equation number 3 in this equation, values of n square and values of value of dn in this equation. So in this equation, so this is, let's say, equation number 1. So we will put equation number 2 and 3 in equation number 1. So let's see what happens. So Ze, so that equation, original equation, is known to us. Now 1/8 into 4 pi into, this is the n square value. So n square value is here. Okay, this is your n square value. N square is twice m L square into L square upon pi square h cross square into E. So now see here, this is 2m raised to 1 half. Okay, this 1 half is came as a multiplier, but it is 2m twice m raised to 1 half. Okay, so into L upon pi h cross. So this is your dn. So we have substituted the value of n square and dn from the equation number 2 and 3 in this equation. Now Ze, which is equal to pi upon 4 into pi upon 4, we can just rearrange these terms properly. See, there are many terms. Okay, first of all, I will show one by one. Let's say, okay, so we will consider this L square upon pi square upon h cross square, and this is L pi upon h cross square. So here we will get this term. Okay, then secondly, this twice m raised to 1 half, this part is there, and there is also twice m part here. So this raised to 1 and this raised to 1 half. So it will become twice m raised to 3 by 2. That part is here. Then okay, so then this 4 pi, so this will be 1 by 2. Okay, so to consider the coefficient now, this 1 by 2 is there, this 4 and this, okay, so 8 is there. So this 4 into 1, that is 4, divided by 8 into 2, that is 16. So 8 ones are, so 4 divided by 16, that is 1 by 4. So this coefficient will be there, and this pi will be there as it is. Okay, so pi is there as it is. Now e raised to minus half, and this is e raised to 1. Okay, that will give me e raised to, so it is written as it is in this step, but in the next step I will write their combination as like this. Okay, and dE as it is. So like this way I have transformed this equation into this equation. Now L cube upon pi square h cross square, that is taken out, 2m upon h cross square, because 2m raised to 3 by 2 is there, upon this h cross square, because this quantity is well known, and in quantum mechanics or in different you can say physical derivations, this constant is always taken together. So how they have done it, I will show it here. So this, okay, so this L 2m upon h cross square is there raised to 3 by 2. So if I write it like this, it will be 2m raised to 3 by 2 divided by h cross square raised to 3 by 2. Okay, so this will be nothing but twice m raised to 3 by 2, that is as it is, divided by this 2 and this 2 will get cancelled and it will be h cross cube. Okay, so that's why this h cross cube, so okay, this h cross cube is used with this 2m and they have written twice m upon h cross square raised to 3 by 2. Understood? So this e raised to 1 by 2 as it is, into this L cube as it is, and this 4 into pi square. This pi square, because this pi cube is there and this pi is there, one pi is getting cancelled, so this pi get cancelled with these 2 and it will become pi square. So we get this equation. So now finally we have equation ZED is equal to 2 pi v into twice m upon h square into e raised to 1/2. So again we will see it, okay, many a times it is represented like this also. So see what happens here. L cube is the volume of the box, because here we have considered this three-dimensional potential box with the length dimensions as L, L and L. So length, breadth and height is L here, length is L, breadth is L and height is also L. That's why it is L cube is equal to, that is the volume of the box, which is V. So this L square is V, that is transformed. You can see here twice m upon h square is there, and this right hand side part is as it is. So here okay, some student may think it is why this 2 pi part came here, but see it carefully. This is h cross square and this is just h square. So you know h cross square is nothing but h upon 2 pi. Okay, so if you substitute the value of h upon 2 pi here, what will happen? I will just show. So twice m raised divided by h upon 2 pi, sorry, I will write it here. So twice m upon h upon h cross is h upon 2 pi, this whole raised to this, its square is there, and the whole raised to 3 by 2 is there. Okay, so when this 3 by 2 comes in, so it will be twice m raised to 3 by 2 as it is, divided by this h raised to, okay, h raised to h cube, it will become h cube here, divided by twice m raised to cube, its cube will be there. So this twice m its cube, this will come in the numerator, and so what will happen? So it will become, so this okay, so at this place if I write the next step, it will be so L cube corresponding to V into, sorry, V divided by 4 pi square is there, okay, into twice m twice pi, sorry, it is twice pi, so twice pi its cube will be there, so 2 cube into pi cube is there. So 2 cube is 8, okay, so 4 ones are 4, 4 twos are 8, so pi square and this pi cube will get cancelled, and I will get this 2 into pi, so 2 into pi into V, this part will be there. So this is the first part, into twice m upon h square is there, raised to 3 by 2, it will be as it is, because this h twice m raised to 3 by 2 divided by h cube is there. If I want to convert it into twice m into twice m upon h square, so I have to do it like this, into e raised to 1/2 into dE, it is as it is. So all of you just do one thing, you write these equations separately on your notebook and get you can say join these steps to one by one, because you may feel that it is simple at this point, but at in the exam you may miss some part. That's why you can do it properly separate. Now density of state, in order to calculate the density of state, we have to consider, we have just calculated number of energy states between E and E plus D, that is ZED. So Pauli's exclusion principle allows us 2 electrons in each state, hence number of electrons, number of energy state actually available are. So these are the energy states, okay, these are the energy states between energy E to E plus D. Okay, these are the number of energy states between energy E and E plus dE. Now if I want to have actually number of energy state number of, you can say, number of energy states, I have to multiply it by 2, because in each energy level there are 2 electrons. That means 2 levels will be available. Understood? So that's why I have to multiply it by 2. So thus the energy states become 2 times this 2 pi v, that is 4 pi v into twice m upon h cross h square raised to 3 by 2 into e raised to 1 half. Just d part is removed. So this question, this is you can say final expression for the calculation of density of states. So I told you, whenever researcher want to do some research, what they do, they first of all put their ideas together, and they try to fit their idea with the experimental results. So if I want to actually plot this equation, so how I can plot this equation, can you tell me? So sorry, I will just let you know. So I think you have studied the equation, like if I have equation like y square, y is equal to let's say x square. This is my expression. So let's say this will be like this equation. Okay, so I think you have studied the equation of parabola. So here you can assume this part as, you can say, a constant into, so sometimes you study it like 4ax square, like this way you have studied these equations. So here what I will do, here ZE is there. Okay, so ZE is there, which is equal to some constant times e raised to 1 half is there. Okay, so what I will do, I will square both the sides. So ZE, this is variable, its square, which is equal to some constant, its square, into e. So this equation is something like this. Suppose I have equation like y square is equal to 4a into x. So this is a parabola which is open towards positive x-axis. If negative sign is there, then it is open towards negative x-axis. So if I plot it here, it will be something like this. Okay, so it will be something like this. But so here we have x means energy, and this is your ZE, that is the density of energy states. But now you must be remembering, ZE cannot take negative values. Okay, ZE cannot take negative values, so only positive values we have to plot. Okay, so even though mathematically it is correct, it should be plotted on the both sides of this E, so only positive values are considered, and this part, this small strip, is D. Okay, so this small strip is D. Now what people have tried, they have tried to you can say match the theory part with the experimental part, but they have observed there is small part that is missing, and that small part is the Fermi distribution function. So this Fermi distribution function gives the probability, so that was not considered while we derived that equation. So here we will consider that. So at t is equal to 0, that Fe is equal to 1 for the all values E less than Ef, that is Ef is the Fermi energy, and it becomes 0 when for E is greater than Ef. We will see how. So let's say okay, so let's say Fermi distribution function f of E at t is equal to 0. Okay, this is all t is equal to 0. F of E is equal to 1 upon 1 plus exponential raised to, so first case is E is less than Ef. If E is less than Ef, this is the case, there will be some negative number divided by, so k beta is positive number into t is 0, that's why it becomes 0. So my negative number divided by 0, that this gives me negative infinity. So 1 upon 1 plus exponential raised to negative infinity, so this gives me 1 upon exponential raised to negative infinity is 0. So 1 upon 1 plus 0, this is 1. That's why the Fermi distribution function has value 1 for t is equal to 0. And second part, for t is equal to 0, f of E is equal to 0 for E is greater than Ef. So let's say t is equal to 0, but E is less than, second case is E is greater than Ef. So if we consider this case, Fermi distribution function f of E becomes 1 upon 1 plus exponential raised to positive number divided by this is 0. So 1 upon 1 plus exponential raised to positive infinity. So exponential raised to positive infinity is infinity. So 1 upon 1 plus infinity, that is again 1 upon infinity. So that gives me 1 upon infinity, that is again 0. So that's why the Fermi distribution function becomes 0 for t is equal to 0 where E is greater than EF. So we will not consider the case where E is greater than EF, because we will consider all the energy levels are, you can say, less than EF at t is equal to 0. So if we attach this part to this density of states, we will get final equation like this. So here you can see originally what happened. Original equation was like this. So I will draw it somewhere so that it will be okay. So let's see, original equation was like this. So this was my energy and this was my ZE, okay, and it was parabolic in nature. But let's say this point is EF, that is Fermi energy. If this is the Fermi energy, so it will go like this, but above that, because this part is E greater than EF, so for E greater than EF, that function becomes 0. That's why if this part is 0, which is attached here, so this will make probability of number of density of states as 0. So let's say this is at this graph is at t is equal to 0. Suppose I have a higher temperature. So for higher temperature, what will happen? For higher temperature, let's say for higher temperature, graph will increase like this, and it will bend like this. It will bend exactly from the half of this height, okay. So this blue colored graph is for t greater than, let's say, 0. T greater than 0, let's say 300 Kelvin. So 300 Kelvin, for 300 Kelvin graph will be like this. If I increase the temperature further, what will happen? This graph will become more and more flat, but finally, sorry, it should not go down, okay. So more and more part from the left hand side can go to the right hand side. So this, let's say, this graph for, let's say, t which is greater than, let's say this is t1, then let's say this is t2, so t2 is greater than t1. So more and more density from the left, it will transfer to the right hand side, and total probability from 0 to infinity, it will become, means it will remain constant, okay. So that is the case. So finally we will get NED, where and density of state as a function of, you can say, electron energy at different temperature. So with this we will, thank you.